Good evening, guys. Today we are going to be discussing the 25th July 2021 JEE Main Shift 1 Chemistry question paper. My name is Prashant and I will be conducting the discussion for you. Let's start off. A quick disclaimer before we start off with the question paper here. The questions which we have collected are based on the memory of the students who attempted the question paper. So obviously there are going to be small errors. We have tried to remove off any questions which we felt had major errors in them to wait for the actual paper when it comes out given by NTA. But for the time being, we are going to be continuing on with what we feel is more or less accurate. Now, let's start off. This is the first question. In the combustion of butane, 72 grams of water is produced. The amount of butane taken initially is going to be how much? The value of this. Okay. So butane is going to be C4H10. So when I'm going to be considering C4H10, they are telling you that the amount of water produced is going to be 72 grams. There are 10 hydrogen atoms in this guy. That means when this guy is burnt in excess oxygen, when I'm burning this in excess oxygen over here, what is going to be happening is I will be having 5 moles of water produced for every 1 mole of the butane in this case. So the idea is very simple. We'll have 1 mole of C4H10 resulting in 5 moles of water. Now, when I'm going to be considering 72 grams of water in this case, this 72 grams of water is going to be having molecular mass as 18. So if I'm having this guy having molecular mass as 18 in this particular case here, the 72 grams of water is going to work out as 4 moles. So 1 mole of this guy produces 5 moles of water. That means 4 moles of water are being actually produced in this case. So if 4 moles of water are produced, how many moles of butane are going to be required here? This is going to be a direct proportion. Obviously, it works out as 4 by 5, which of course works out as 0.8 moles of butane. So I'm going to be having 0.8 moles of butane required to produce 72 grams of water in this particular case. Okay. Now if I have 0.8 moles of butane, in this case they are telling us in a very ambiguous manner amount of butane. Obviously my expectation is that in the actual question paper it was quite clearly given the amount or number of grams of butane required, because I'm going to assume that the amount over here stands for number of grams. Amount, when it is generally given, can be understood to be either moles or grams. But the default thing which you have to assume, if they have given as amount in the JEE Mains exam, the default assumption which students should be making is grams. At least with respect to chemistry, the default assumption which students should be making is grams. Now, so in this case, if I'm going to be considering this as number of grams, so if I'm considering this as number of grams in this particular case here, 0.8 moles of butane is a setup here. So number of grams, if I want to convert it, I'll have to do it like this. 0.8 into molecular mass of C4H10. C4H10, what is the molecular mass? Carbon is going to be 4 into 12 in this case, because atomic mass of carbon is going to be 12 here, of course, and there are 4 carbon atoms. So it works out as 4 into 12 plus, of course, 10 into 1, which translates to become 48 plus 10, which works out as 58. So I'm going to be having 0.8 into 58 in this particular case. Okay, it looks ugly as 88 over here. So let me just erase that part off slightly. So it's supposed to be 58. Okay, so we're going to be having it as 58 in this particular case. So 0.8 into 58 is going to be how much is the question over here. So 0.8 into 58 works out as 46.4. Alright, so it works out as 46.4. They are telling us that the amount of butane is supposed to be written as x into 10 power minus 1. So if it's supposed to be written as that, this is supposed to be equal to x into 10 to the power of minus 1. That means in this case, value of x works out as 464. This is basically going to be your answer for this particular question here. So whenever the JEE Mains from last year's cycle onwards, when I say last year cycle, I mean September of last year cycle onwards. Alright. So since then, every round the JEE Mains has conducted, they have tried to make the questions without unnecessary decimal points wherever possible. So what are they doing? They are basically making the question in this format. They are trying to basically remove the decimal places within the question itself. They give something like that. Anyway, so in this particular case, the answer is going to be x works out as 464 in this particular case, which is going to be the answer for this first question. Now let's get to the next one. Okay, A plus B is in equilibrium with 2C. Initially, 1 mole each of A, B and C are taken in a 1 liter vessel. Equilibrium constant is given as 100. Okay, the concentration of C at equilibrium in x into 10 power minus 1 units, again the same kind of scenario. When there is a decimal point which comes up, they try to remove the decimal point and ask the question. The value of x is going to be. Now another point to pay attention to here is physical chemistry questions are mainly being tested in numericals like this, all right, in the last section where there is a choice in questions. So the student is obviously having choices over here. When the student has a choice, they can pick whichever topics they are more comfortable with. Anyway, coming back to the question here. A plus B is going to be in equilibrium with 2C. Initially 1 mole each of A, B and C are taken in 1 liter vessel. So we are going to be having A plus B in equilibrium with 2C. Okay, so we are having initially 1 mole each in a 1 liter vessel. Equilibrium constant is given as 100. So let's start off at time t equal to 0. So at time t equal to 0 in this particular case here, I am going to be having 1 mole each in 1 liter vessel. So concentration of each of these is going to be 1. Now equilibrium constant is given as 100. So let us first calculate what is the Q for this particular case here. The QC at time t equal to 0 is going to be, so at time t equal to 0, QC is going to be 1 squared divided by 1 into 1, which of course works out as 1. Equilibrium constant though is 100. So I am going to be having Kc value given as 100 in this case. That means the QC is going to be less than Kc in this particular case here. So we are going to be having QC less than Kc, which means reaction is going to be moving in the forward direction to increase the QC value. So that is the direction in which the reaction is going to be moving in. So if the reaction is going to be moving in that direction, what can I say here? At time t equal to equilibrium. So at the equilibrium condition, how is the situation going to be changing in this case? So at the equilibrium condition here, I will be having this as say 1 minus x. This is going to be 1 minus x. And this will work out as 1 plus 2x. Because for every x amount of A and B consumed, 2x amount of C is going to be actually produced in the reaction. So when you're going to be having this as the scenario here. Now in this case here, instead of taking it as x over here, a better variable would have been something else because they have given this as x over here. But chalo, it doesn't really make much of a difference. So in this particular case, how to proceed and solve over here, you're going to be having, this is at equilibrium. They have given us that the equilibrium constant is 100 in this particular case. So what can I put over here? I'm going to be having it as, in this particular case, I'm going to be having 1 plus 2x whole squared divided by 1 minus x whole squared works out as 100, which obviously tells me that I'm going to be taking square root in this particular case. I'll be having it as plus 10 or minus 10. Logically speaking, you should check out for both values of plus 10 and minus 10 what you're going to be getting as answer. One of them will not be consistent with the setup. What do I mean by consistent here? They have told us that there is only 1 and 1 of each of A and B. So x cannot be more than 1. If x is more than 1, that is not meaningful in this particular case here. So x has to be less than 1 when you're solving for it. Now anyway, coming back to the point here, when you're going to be doing it, it will work out as 1 plus 2x divided by 1 minus x. We can take it as either plus or minus 10. When you're going to be solving here, how to proceed over there, I'm going to take it as plus 10 in the first case here and show you how to proceed there. So it works out as 1 plus 2x works out as 10 minus 10x. Bringing it to this side, we end up having in this case 12x working out as 9, meaning x works out as 9 by 12, which works out as 3 by 4. So if x is going to be 3 by 4, they are asking us what is not the, this particular thing is going to be concentration of C, which is asked here. Concentration of C is 1 plus 2x. So if it's 1 plus 2x, we can effectively write concentration of C. In this case, as you can see, x is 3 by 4, which is consistent with this data. If I take it as minus 10, I will not have it as consistent. Let me show you that case as well. When you are taking it as minus 10 in this particular case here, what do you end up having in that scenario? So if I take it like this, what happens is 1 plus 2x works out as minus 10 plus 10x. So if I bring it to this side, it will work out as minus 8x is equal to minus 10 is going to be on that side and a plus 1 is on this side. So when I'm going to be bringing it to that side, it works out as minus 11. And as you can see, x works out as 11 by 8, which is greater than 1. If it's greater than 1, it is inconsistent because the maximum value of x has to be 1. It can't be more than 1. So this part over here is not going to be applicable at all in this case. Why is it not applicable? Simply because it is going to be something which is an inconsistent data. So I don't need to worry about this. This results in inconsistent answer. So when you're going to be considering any scenario where you're taking square root, you should generally, mathematically speaking, check for both cases. One of them will work out inconsistent, one of them will work out consistent. That's the way to proceed. Anyway, coming back to this question here, let's finish up with this. So x is going to be 3 by 4 now. Concentration of C is going to be 1 plus 2x, which of course works out as 2x now. It works out as 0.75, 1.5, so it works out as 2.5. That is written quite miserably, so let me just change this off slightly. Okay, so concentration of C works out as 2.5 over here. They are telling us that we need to put it as x into 10 power minus 1. So this works out as the final answer into 10 to the power of minus 1, which means answer for this question works out as 25, which is what we have got as well. So this is for the second question in this case. Let's get to the next one. In the leaching of bauxite, which oxide is leached out using sodium hydroxide? This is actually an easy question, but there is a small controversy if the options given are as they are given. Now, why am I saying there's a tiny controversy in this particular case here? When you're going to be having leaching done using sodium hydroxide, this is going to be a process which is referred to as Bayer's leaching. Now, when we are going to be considering Bayer's leaching here, we are going to be leaching out alumina and the impurity which can dissolve in sodium hydroxide. Usually in Bayer's leaching here, we are going to be having the following setup. The ore is going to be Al2O3, whereas I am going to be having the main impurities are going to be FeO and silicon dioxide. The problem here is this: when I am going to be dissolving it in sodium hydroxide, let's say I am taking this mixture, if I dissolve it in sodium hydroxide, concentrated NaOH, and let's say heating. If I am going to be having this done here, what happens is the Al2O3 ends up dissolving, forming AlOH 4 times minus 1. At the same time, the silicon dioxide also ends up dissolving. Alright, so you're going to be having the alumina also dissolving. It forms either AlOH 4 times minus 1, or you can think of it as AlO2 minus 1. Either way is the same thing basically. One is with water, one is without water. Now, the same way, silicon dioxide will also end up dissolving because this is an acidic impurity. So, being an acidic impurity, it will certainly dissolve in basic medium. That is why I said there is a small controversy in the question. Either way, they are asking the oxide which is leached out. When they are saying leached out, that means they are eventually considering the entire process. When you are considering the entire process, the best answer is going to be Bombay. So, when this question is given, like in today morning's paper or in 25th July morning paper, if it is given, you will have to basically choose Al2O3 as the best answer in this particular case. Yes, impurity silicon dioxide is also going to be leached along with the Al2O3, but we can remove the impurity by selective precipitation later. How do we remove the impurity by selective precipitation? We take the mixture. If I am taking silicate over there, what is the SiO2 going to be forming? SiO2 also forms something similar, wherein you are going to be having the SiO4 4 minus basically going to be formed over there. It ends up forming the silicate ion in that particular case. That silicate ion is going to be applicable here. Both of them are going to be water soluble systems. So, this silicate ion and the aluminate over here, both of them are going to be present. How do I make sure that only one of them gets out? I end up passing carbon dioxide gas through it. When I end up passing carbon dioxide gas through it, only the aluminum hydroxide precipitates out. Why is that going to be happening? Because carbon dioxide is going to be a stronger acidic substance compared to the aluminum over here. Whereas it is a weaker acidic substance compared to the silicon in this particular case here. When you're looking at the acidic nature of carbon dioxide and silicon dioxide and aluminum oxide, Al2O3, SiO2 and carbon dioxide here, carbon dioxide is in between the three of them, where aluminum oxide Al2O3 is going to be exhibiting the least acidic character, silicon dioxide will show the most acidic character among these three over here. Carbon dioxide will be in the middle. So carbon dioxide can displace Al2O3 from the solution in a basic medium, but it cannot displace the silicon over there. So what happens in this particular case is very simple. We will have carbon dioxide displacing the aluminum, AlOH thrice gets out as a precipitate. This comes out as a fresh precipitate. This precipitate on further heating will produce me Al2O3 pure. That is basically the method of Bayer's leaching in this particular case here. The silicon dioxide remains in solution as the silicate over here. Why does it remain in solution? Because silicon dioxide is a little bit more acidic than carbon dioxide. Why so? Because silicon is going to be having empty d orbitals. That is what makes it slightly more acidic compared to the carbon dioxide here. Anyway, so in this case the silicon remains in solution, aluminum gets out, gets precipitated, which on firing up and heating strongly will give you pure Al2O3 in this particular case here. So this process of precipitating the aluminum hydroxide is called as seeding of aluminum hydroxide. Anyway, coming back to the real point here, the point here is there is a tiny bit of a controversy in the question, but the best possible option to choose would be Al2O3 in this particular case here. I will agree that silicon dioxide will also dissolve. So technically speaking, in the chemical leaching process, in the first step, silicon dioxide is going to go into solution as well. But throughout the entire process, we will leach out only the aluminum. Alright, so we are not going to be leaching out the silicon in the process. The silicon is removed out as impurity in the process. This is a way to remove the silicon here. Okay, so let's get to the next one. Among the given oxides, CrO3, V2O5, Fe2O3 and MnO2, the correct increasing order of oxidation state of metal is. This is an easy question. So we are going to be having the following oxides available. CrO3, here chromium is of course going to be in +6. Vanadium pentoxide, V2O5, vanadium is in +5. Fe2O3, iron is going to be in +3 oxidation state here. MnO2, manganese is in +4 oxidation state here. So I am interested in arranging them in the increasing order of oxidation state of the metal over here. So if I am interested in arranging them in increasing order of oxidation state of metal over here, what is the increasing order of oxidation state? Fairly straightforward. Fe2O3, which is the +3, is the lowest oxidation state. They are asking for increasing order, so we need to go from lowest to the highest. So Fe2O3, then we will end up having manganese dioxide, which is in +4. Then I will be having vanadium pentoxide, which is going to be having a +5. Lastly, I will have CrO3, which is going to be having a +6. So we are going to be having this as the increasing order here, which basically translates as 3 less than 4 less than 2 less than 1. So which option is going to be the best option here? So we need 3 last, or 3 are the first, 4, 1, 2 and 1. 3, 4, 2 and 1 now. We are having this guy as the best option here. So 3, 4 less than 2 less than 1. Answer is Delhi in this particular case, or the fourth option in this particular question. This is one of the freebie questions, I suppose. A very straightforward, very easy question. How did I calculate the oxidation state? Oxygen is always more electronegative compared to the metal. If it's more electronegative, it has to be given the negative oxidation state. Whenever oxygen is present in a system, generally, as long as it doesn't have any weird peroxo bonds or such things, you will have oxygen having oxidation state as -2. So for instance, let me quickly explain for one of these cases. You're going to be having net is 0. So net is 0 now. 0 is going to be chromium plus 3 into -2, meaning chromium works out as +6. That's the idea here. So you're going to be having this as the methodology basically. This is a fairly easy question. Next one. Find the concentration of iron plus 2. 10 ml of iron plus 2 is what we have over here. Required to reduce 15 ml of 0.1 molar K2Cr2O7 solution. So first of all, we are going to be having reduction of dichromate happening in this case. So dichromate, what is the reaction which happens? Cr2O7 2 minus is going to be having chromium present in +6 oxidation state. This dichromate is going to be becoming chromium +3. So when it ends up becoming chromium +3 in the process, what is going to be happening here? What is the N factor for the dichromate in this case? So the dichromate in this particular case is going to be having +6 to +3 change happening here. There are 2 chromium atoms, so each of them is going to be having a change of 3 because +6 to +3 na per chromium change is 3. So I'm having 2 chromium atoms, net change is going to be +6. So the N factor for this guy works out as 6. Okay. So they have given us 15 ml, 0.1 molar in this particular case. The basic principle is very straightforward. We are going to be having milliequivalence of oxidizing agent is equal to milliequivalence of reducing agent. In this case, the oxidizing agent is of course going to be your dichromate and the reducing agent is going to be your iron +2. Dichromate, we have found out the N factor as 6. Iron +2, what is the iron +2 going to become in the process here? Iron +2, when it is undergoing oxidation, it is acting as a reducing agent here, correct? Reducing agent will undergo oxidation in the process. So when the iron +2 undergoes oxidation, it will end up becoming iron +3. So when the iron +2 becomes iron +3, what is going to be the N factor for this fellow here? The N factor for this guy works out as 1. Because the change in oxidation state is only 1 over here. +2 to +3, only one ion is available, N factor is 1. So this guy's N factor is going to be 1. Now what does milliequivalence of oxidizing agent equal to milliequivalence of reducing agent mean? Basically it means number of millimoles of electrons transferred have to be the same in both sides because this guy is going to be losing electrons, this guy is going to be gaining electrons. So effectively what does this statement translate to? It translates to number of millimoles of electrons lost by the reducing agent are equal to the number of millimoles of electrons gained by the oxidizing agent. Alright, so millimoles of electrons, instead of thinking of it as milliequivalents, you can imagine it in your brain as millimoles of electrons lost by this guy, gained by this guy. Both have to be the same because a transaction has happened. Now let's have a look now. How do we go about it? We are going to be having in this case, we have got the N factor. What else do we have? We have 15 ml available and we are having 0.1 molar. For this guy, I know it is 10 ml. I do not know the molarity. That is my variable in this case. So I need to calculate the molarity in this particular case or concentration in this case as they have mentioned. So concentration is basically molarity. Now, so in this particular case here, we are going to be solving for it directly. So number of milliequivalents, we will have it as number of millimoles multiplied by N factor. So millimoles is going to work out as volume in ml into molarity. So if I have to put it up, it will be like this. So volume in ml multiplied by molarity. This gives me millimoles. This fellow multiplied by N factor will basically translate into milliequivalents. So in this particular case, this is the general formula which I am going to be applying. So if I am going to be using this, what will I effectively translate this into? 15 into 0.1 into 6 is going to be equal to 10 into 1 into molarity x. So I need to calculate that x over here. So x works out as 15 into 0.1 into 6. Now it works out as of course 0.6. So we'll have this basically cancelling off 2. This will work out as 3. So we're going to be having this 2 and this 6 will basically go off. This will work out as 3. So 0.1 into 3 into 3. 3 into 3 is 9. So 0.1 into 3 works out as 0.9. So I'm going to be having in this particular case here, the answer for this particular concentration works out as 0.9. So concentration of iron +2 is going to work out as 0.9 molar. Now I'm not sure how the question was asked in this case here. Did they want an integer answer? Did they want or did they give it as x into 10 power minus 1? I'm not sure. So I'm not going to comment on that part over here, depending on the actual instructions given in the JEE mains paper and any tiny change in the question as it was given, or if it is not given, if there is no change, answer is supposed to be given as 0.9. But my guess is there will probably be some way in which they have adjusted the question slightly here or there to make the answer as either 1 or 9 depending on how the question was framed. So the answer for the question as of the question which we have at the moment, answer is 0.9 molar. I hope you guys understood how the solving works. arrange the following ions in the increasing order of size. So we have sodium plus, we have potassium plus, obviously that's supposed to be aluminum 3 plus over here, and we have magnesium 2 plus. So we're going to be having Na plus, K plus, magnesium 2 plus and aluminum 3 plus. So first let's look at the number of electrons in each of them. Na plus, magnesium 2 plus and aluminum 3 plus. All three of these guys are going to be having, in this particular case here, they'll be having neon configuration. When they have neon configuration, they'll have 10 electrons. Okay, so they're going to be having 10 electrons in this particular case here. So they're going to be having 10 electrons in this case. The sodium is going to be having 11 protons. The magnesium is going to be having 12 protons. Aluminum is of course going to be having 13 protons. So you're going to be having, each of these is going to be having different number of protons. So among these three, we can easily arrange the sizes here. What is the arrangement of sizes here? More protons, if they are having same number of electrons, greater the number of protons, greater the nuclear force of attraction, which means smaller size. So we're going to be having aluminum plus 3 smaller than magnesium plus 2 smaller than Na plus. This is when I'm comparing Na plus, magnesium plus 2 and aluminum plus 3. When I bring K plus into the factor, K plus is going to be having argon configuration. So this guy is going to be having 18 electrons in this particular case. But of course, it is also going to be having 19 protons. So you're going to be having the size of K plus being larger compared to the size of Na plus itself. Alright. So K plus is going to be larger than Na plus. Why? Because down the group size increases. As simple as that. So this is going to be down the group size increases. That's the basic principle here. So if I'm going to be using that periodic trend here, I will be having Na plus being smaller than K plus. So this is the increasing order of sizes. What are they asking? Arrange the following ions in the increasing order of size. So this is going to be the order we are looking out for. So aluminum plus 3 has to be the smallest. So this is fine, this is fine, this is fine, this is fine, this is wrong over here, this is fine, this is fine. This is wrong of course, this is wrong of course. So answer in this case is option 1 in this particular scenario here. So we're going to be having, this is the order over here. How do we go about the order? We first compare stuff which is going to be having same number of valence electrons, same number of total electrons. Then we end up comparing with the other fellow there. So first comparison is with these three over here. Then we introduce potassium plus into the setup to see where it will rank among these. Okay, next. Henry's law constant for carbon dioxide in water is going to be given as this. How many millimoles of carbon dioxide would dissolve in 0.9 liters of water? Assume carbon dioxide gas exerts a partial pressure of 0.853 bar. Okay, let's have a look at this question now. Let's proceed into the question here. So we're going to be having in this particular case here, Henry's law constant for carbon dioxide in water has been given with the units as bar. That is an important distinction to make over here. Now, why am I saying that is an important point to pay attention to? Because Henry's law constant is going to be deciding what is going to be the way in which we are going to be having the law seen over here. Now, what do I mean by that in this particular case here? Henry's law can be looked at as partial pressure of gas is going to be equal to Kh into chi of gas. This is one way of looking at the Henry's law statement. Another way of interpreting the same statement works out as partial pressure of gas into chi is going to be equal to Kh. So we can effectively interpret it in different ways over here. Effectively, the idea is partial pressure is proportional to chi or chi is proportional to partial pressure. So the other way of writing it is like this. Chi of gas is going to be equal to Kh into partial pressure of gas. Both are meaningful interpretations. We need to decide which is the interpretation based on the units of this particular Kh which is given to us. The Kh in this case is going to be having units as bar. So if the Kh is going to be having units as bar, this is my correct representation which I am going to be using. This representation is not valid here. It doesn't mean this is not, going to be used in some questions. In some questions, in both JEE Mains and JEE Advanced, they have used this notation of Henry's law also. Both notations are going to be seen depending on the question and the units of the kH which have been given. You need to choose which is the correct representation to apply over there. Coming to the point here, kH is going to be in bar, so this is the representation we are going to be having. Why? Because this is dimensionless. So this is dimensionless in this particular case, which means I don't really have any dimensions for it. So whatever is going to be the partial pressure dimension, kH will also take in this case, which is what bar is basically telling us. Okay. So partial pressure of the gas has been given as 0.853 bar. So we can effectively write as 0.853 bar, which is partial pressure of carbon dioxide above solution. This is going to be equal to kH into chi. kH has been given as 0.835 into 2 into 10 power 3. So it is going to be 0.835 into 2 into 10 power 3 multiplied by chi of gas. Here is where things get a little bit more interesting. 0.9 liters of water. What is meant by 0.9 liters of water in this particular case here? When you are going to be considering 0.9 liters of water over here, first off, let's translate that into how many ml. This of course works out as 900 ml. Now in this case here, we are having mole fraction of gas. This mole fraction of gas is basically going to be nothing but number of moles of gas dissolved divided by N of gas dissolved plus number of moles of solvent. So I need number of moles of solvent in this case. Number of moles of solvent is going to be something which requires mass of solvent. So I need to make an assumption here. What is the assumption I'll be making here? I am going to be making a simple assumption that the density of water is going to be 1 gram per ml. This assumption is generally accepted in both JEE Mains and JEE Advanced when you absolutely have to use it. Avoid using the assumption as much as you can, but if there is no other option, use it. In this particular case here, density I am taking as 1 gram per ml, which effectively translates to 900 grams of water. Molecular mass of water is 18. So this works out as 900 divided by 18, which of course works out as 1800, meaning it works out as 50. So we're going to be having 50 moles of water in this particular case. So if I'm having 50 moles of water, let's assume that they're asking what over here, they're asking how many millimoles of carbon dioxide. How many millimoles of carbon dioxide would dissolve. So let's assume that the number of millimoles or the number of moles is going to be X over here, or we can take it in millimoles also. It doesn't make much of a difference because as long as I take everything in millimoles, it will anyway get cancelled over here. So let's proceed here. So let's assume that this is going to be X in this case, millimoles of carbon dioxide, which I need to calculate. I'm going to take it as X. So I'm going to be having it as this entire thing is going to be multiplied by X divided by X plus 50 moles translates to 50,000 millimoles. So now in this case here, I am assuming there is a tiny issue in the question. When the student was asked, probably my expectation is this was given as either 0.853 or this was given as 0.835, such that things will cancel out beautifully. Otherwise they won't have a meaningful question here. They will try to make sure that it is getting cancelled out over here. That is my expectation in this case. Now in this particular case, meaning these two are expected to cancel out over here, so that there is going to be a direct cancelling off. Now we can effectively get to an answer more efficiently. This will basically result in these two getting cancelled, meaning I will end up having in this case X divided by X plus 50,000. X is going to be much lesser than 50,000 in this case, meaning we can effectively say 50,000 plus X is approximately equal to 50,000. Substituting, we will end up having X divided by 50,000 works out as, bringing this to the other side, it will work out as 10 power minus 3 divided by 2, or rather 10 power minus 3 into 1 by 2, which works out as 0.5. Solving, we will end up getting the value of X. So X works out in this particular case as 50,000 into this. So 50,000 into this, now this is 5 into 10 power minus 4. So 5 into 10 power minus 4 into 50,000. All of these will go off, so it works out as 25. So answer works out as 25 in this particular case here. As I said, some tiny assumptions need to be made to get to a more simpler and more meaningful answer. See, these kind of assumptions, you can't be taught to make these assumptions. You can basically get into a habit of making these assumptions when you solve and practice more old JEE mains and JEE advanced questions. That is basically the trick here. Let's get to the next one. Which of the following does not exist? This is a very interesting question. Of course, you can answer it based on facts, but you can answer a question like this based on logic and knowing some information as well. For instance, this does exist. How do I know this exists? You guys might be familiar with the fact that HF can dissolve glass. How is it that HF dissolves glass? When HF is going to be reacting with silicon dioxide, which is basically glass, you're going to be having SiF4 produced first. That SiF4, when it is going to be reacting with excess HF, will effectively end up forming SiF6 2-. It actually forms H2SiF6, which is soluble. So this definitely does exist. So this is going to be a wrong option. Next, we are going to be having 3 options given to us. Let's start ruling out. When you're given a question like this, when you don't have the exact information available with you, how do you judge based on logic? That's what I'm interested in going for over here. So this is a first option which I've already ruled out as the answer. Excellent. Let's go for the 4th option now. This is going to be something where the tin is present in +4 oxidation state. When I'm considering tin in +4, it is obviously going to be amphoteric. Tin is going to be in the P block. It's in carbon family, and you're going to be having it in +4 oxidation state, which is a fairly high oxidation state. Whenever you are going to be having something like a metal in +3 or +4, it will generally exhibit amphoteric character. Of course, there are exceptions to it. You are going to be having beryllium +2, zinc +2 showing amphoteric character in +2 itself. And iron +3 will not show any amphoteric character, it will only show basic character. But a generalization which you can use is +3 and +4 metal ions will usually show amphoteric character. Which means if I am going to be having tin in the form of SnO2, where tin is in +4, when I am going to be dissolving it in excess concentrated sodium hydroxide, it has to end up forming that complex. There is no other way around for it because it is an amphoteric oxide. It has to dissolve with the sodium hydroxide to form a complex. What will it form? It will effectively go for SnOH 4 times first. Because what is SnO2? It is an anhydrous form of SnOH 4 times. This will end up reacting with 2 more OH minus to effectively end up forming SnOH 6 times 2 minus. Now, you can also think of this in a slightly different manner. How else can you think of this? You can think of this SnOH 6 times 2 minus as SnO3 minus 2. That is another way of interpreting the same thing over here. So you can think of, one second guys, yeah. You can think of this SnOH 6 times 2 minus as removing out 3 water molecules and left over is whatever is left over. You can think of it as this. This is going to be stannate ion in this particular case. Alright, it is called a stannate ion, which is nothing but dehydrated form of this fellow here. So obviously this also exists. So this is also existing now. This is also wrong. Now we have got 2 options. We are down to 2 options right now. When you are down to 2 options, job becomes much easier. Alright. Now if I have to pick among these 2, let's have a look now. When you are considering the carbon family, we are having carbon, silicon, germanium, tin and lead. So when I am going to be having carbon, silicon, germanium, tin and lead, I am going to be having, as I go down the group, size increases. That's the basic idea here. Now, when you're going to be comparing both of these guys, size increases and furthermore, metallic character also increases. Both are important factors here. Let me explain why. So first off, when you're going to be having these 2 taken, SiCl6 2 minus and GeCl6 2 minus, there are 2 problems there. When you want this kind of a scenario to form, The first issue is you should have enough space around the central metal atom to arrange 6 atoms. For instance, in this case, how is this capable of forming? There are 2 reasons why the SiF6 2- forms. First reason is F- is smaller in size. Because it is smaller in size, it can surround the silicon atom more comfortably. Now, if I am going to be applying the same for Cl- over here, Cl- is a much larger anion because F- is going to be above Cl- in its period or in its group rather, sorry. So, you are going to be having the Cl- is being larger in size compared to F-. Because of that, this is going to be more difficult to exist compared to the SiF6 2-. Now, let us check out the other factor. Fluorine is going to be highly electronegative. So, it can basically force the central fellow into reacting as well. Cl is less electronegative than fluorine, so its ability to force is not that much. So, when you are going to be comparing silicon and germanium, the metallic character for germanium is higher, which means the electronegativity for silicon is actually higher. That means silicon is more electronegative than germanium, which basically tells me that it is more difficult for chlorine to force the silicon into forming this than the germanium. Another reason why we are going to be having SiCl6 2- being more complicated or more unstable is because silicon is smaller in size. When the silicon atom is smaller in size, it doesn't have enough space around it. That is the simple reality. For instance, let's say I am going to be having basketballs. Let's say I am trying to surround myself with basketballs. How many basketballs can I surround myself with? It depends on my size over here. If I am taller and more heavily built and more having more surface area, more basketballs can basically cover me, or more basketballs can be made to touch my skin. That's basically the same principle here. So, in this case here, silicon being smaller in size will find it more difficult to be surrounded by the Cl- ions, whereas the germanium will find it more comfortable because it is more larger in size. So, among these two, this is worse off. Alright, so if this is worse off, the best answer has to be SiCl6 times 2-. So, in reality, I can tell you that this will exist, this does not exist. That is fact, that is fact. You can answer this question based on fact or based on logical analysis. Logical analysis, you will have to go via the method which I just showed you. That is the general idea which will help you to connect all of the pieces in this case here. Method is going to be something which will take a bit more time. I will be honest with you in this question, if you know the information, it is always faster. Inorganic chemistry questions are going to be the major time savers for you, where you can save time in the chemistry part and invest it in either physical chemistry questions or mathematics or physics. So, it is always better to remember, but if you don't remember, this is the way to logically arrive at the answer. I hope this was interesting and clear. Let's get to the next one. So, answer for this question is obviously option Bombay here. This will exist. Why? Because it's definitely more stable compared to this guy. So, among the options here, this is definitely the best option here. Coming back to the next one here. Which of the following complex is active in magnetic field? What does active in a magnetic field mean? Active in magnetic field, it is going to be either paramagnetic or ferromagnetic. That is basically the idea here. In this case here, obviously for a complex, we are not talking ferromagnetism, we are mainly talking paramagnetism. So, this is not part of our conversation right now. So, paramagnetic is what we want. So, paramagnetic, now what does that lead to? It leads to unpaired electrons being present. Let us talk about each of these guys here. FeH2O 6 times 3 plus. This is going to be iron plus 3. So, if it is an iron plus 3 case here, this is going to be having a configuration of D5. So, iron plus 3 is going to be forming a complex with H2O over here. H2O is a weak ligand. Weak ligand, now what is going to be happening here? This will basically be an sp3d2 config. Alright. So, I will be having 3d5, having 1 electron like this. This is my 3d5. 4s. So, this is going to be my 4s, 4p, and I will of course have 4d. So, I will be having the water dumping a pair of electrons here, one more here, one more here, one more here, one more here, and one more here. all of these will hybridize, resulting in my sp3d2. So of course there are 5 unpaired electrons. So of course answer is first option. Let's quickly confirm for the remaining over here. COCN 6 times 3 minus. Let me just show you how it works for each of the other 3 cases. Cobalt plus 3 is a D6 configuration. So if I am going to be having the D6 configuration here, cyanide is strong ligand. So we'll have pairing up happening in this case. This will basically work out as something like this. So this is going to be my T2G level, this is my EG level of my 3D. Then I'll have 4S, then I'll have 4P. So we'll end up having 1, 2, 3, 4, 5 and 6. We'll have 2 electrons from cyanide, 2 electrons from cyanide, 2 electrons from cyanide, 2 electrons from cyanide, 2 electrons, 2 electrons. So this will effectively work out as a D2sp3 hybrid. And as you can see, no unpaired electrons. So this is going to be diamagnetic. This is of course going to be paramagnetic. NiCO 4 times, NiCN 4 times 2 minus. This is going to be something which will be working out as a D10 config. And it will work out as sp3 hybrid. And it will of course work out as diamagnetic as well. Whereas the NiCN 4 times 2 minus, this will work out as a square planar complex, which will be DsP2 hybrid, and it will end up having a D8 configuration. And of course, it is also going to work out as diamagnetic. So we are going to be having the last 3 options, second, third and fourth option working out as diamagnetic complexes. The first one works out as a paramagnetic complex in this particular case here. So I'll show you for one of the other 2 examples as well, because I have just space enough for one of them. I will show you for the NiCO 4 times here. It is going to have 4s2 3d8, which will basically change into a 4s0 3d10. Why will it happen? Because the carbon monoxide is a strong ligand. So we are going to be having carbon monoxide capable of synergic bonding. So it will empty the 4s over here. 4p is also going to be empty. So what happens? This is my 3d. The 3D will have fully filled config. All of these electrons are going to be from the nickel itself. The 4s will be empty, the 4p will also be empty. What will happen? The carbon monoxide will dump its electron pairs there. So the crosses represent the electron pairs from the ligands, the up and down spins represent the electrons which are present from the metal atom or metal ion in the center. So this is of course going to work out as an sp3 hybrid. Tetrahedral structure. The last case I am leaving it to you. I have already given you the configuration and the setup there. So in this case answer is going to be option 1. Let's get to the next one. Empirical formula of a given octahedral complex is CrCl3, 3NH3 and 3H2O. So this is the empirical formula given. They are quite clearly telling you of a given octahedral complex. Octahedral complex is what they are giving. It precipitates 3 moles of AgCl. Okay, what is the secondary valency of the central atom in this particular case here? Now, what is meant by secondary valency? Secondary valency is going to be nothing but number of coordinate covalent bonds formed. So if I am looking at number of coordinate covalent bonds formed, first I need to arrive at the complex, but in reality I don't need to. They are quite clearly giving us octahedral complex. Octahedral basically straight away tells me 6 ligands are used, which automatically gives answer as this. But for the sake of solving, let me show you how the complex should be. You are going to be having Cl3, 3NH3, 3H2O. They are telling us precipitates 3 moles of AgCl. When it is precipitating 3 moles of AgCl, what does that translate to? This translates to the following information. This means that 3 Cl minus ions are present in ionization sphere. So if 3 Cl minus ions are present in ionization sphere, what is the formula of the complex in question here? It has to be Cr NH3 thrice, H2O thrice and I am going to be having a Cl thrice here. This is going to be the formula for the complex, where this is going to be a net plus 3 in this case. Now, you will see that the formula for this complex is given slightly differently in certain cases, but depending, I am basically basing my answer on the question given. In the question, they have quite cleanly given octahedral. We are not expected to question the question here. We are expected to answer according to the question which is presented in front of us. So, in this case here, I will be going with answer as option 4, which is going to be giving me secondary valency as 6 in this particular case here. Why? Because the chromium in the center is going to be accepting 6 lone pairs from 6 liganding molecules. So, this chromium plus 3 accepts 6 lone pairs from 6 ligands, and that is why it is going to be resulting in octahedral structure or octahedral complex. If it was only accepting say 4, it will end up becoming tetrahedral, or it might be square planar. 3 and 1 obviously is not going to be possible in this case. So, this is going to be your 10th question. Let us get to the next one. For a process, okay, it is very badly copied and pasted over here. Let me just explain the data first. So, enthalpy of fusion has been given as 2.4. Of course, I am guessing it is going to be kilocalories per mole. And the other data which is given is enthalpy of vaporization. That has been given as 98.6. Of course, kilocalories per mole. Very easy question though. They are asking us what is enthalpy of sublimation. All you need to understand is what is sublimation. So, if I am going to be considering a solid, let us say is going to become a liquid, and then the liquid ends up becoming a gas. This process is called as fusion, and this process is called as vaporization. But if I did this same process in one shot directly between these two guys over here, if I did this between these two directly over here, this is called as sublimation. And the basic principle is very straightforward. Enthalpy change is a state function, which means we can apply Hess's law. What does the law basically come to? We can say that this sublimation is going to be both the summation of fusion and vaporization. So, I can write enthalpy of sublimation is going to be nothing but delta H fusion plus delta H vaporization. So, if it is going to be delta H fusion plus delta H vaporization, it quite obviously works out as 2.4 plus I am going to be having 98.6. which works out as 98 plus 200, 100 plus 1, 101. So, the answer is going to be 101 in this particular case. So, this is going to be the answer for this particular question over here. So, 101 kilocalories per mole is going to be my enthalpy of sublimation for this particular substance. Let us get to the next one. Very simple, straightforward question. This is a must attempt question, very straightforward question, because it will save you a lot of time from a physical chemistry point of view as well. Which of the following statements is correct? Okay, alright. HH bond strength is equal to DD bond strength. This is wrong. This data is available in your NCERT textbook as bond dissociation energy or bond energy of H2 and D2. This is available in NCERT. NCERT, where is it available? It is available in hydrogen chapter in class 11 NCERT. And it is available in a tabular column, by the way, where they discuss properties of H2 and D2. So, the values, this is around 434, this is around 450, approx, of course. So this is pure data based. There is no clean logic which will be able to explain things perfectly over here. Logic is going to be nothing but an excuse in this particular question. It is not going to be directly leading to the answer, but in retrospect, if you know the answer, you can make up a logic which will sound correct. But there is always going to be other conflicting logics which can cause trouble in these kind of questions here. So in these kind of questions, it is highly recommended that you depend on the data which is available in NCERT textbook, which is perfectly in the domain of your syllabus. You should know it. So it's available in NCERT textbook, class 11 NCERT, hydrogen chapter. It is available in a tabular column which compares hydrogen and deuterium properties. It is basically going to be in bond energy, or you can think of it as bond dissociation energy. So obviously deuterium bond dissociation energy is going to be greater than that of hydrogen. So if it's going to be this way, we'll end up having HH bond strength is less than DD bond strength. This is the correct statement. So in this case here, the correct option is going to be the fourth option in this particular case here. Next. Which of the following about micelle formation is correct for sodium stearate? They have given us the formula here. Sodium stearate can be considered as some long chain carbon ending, which is going to be C14H35, and we'll have an ionic ending, which is going to be my CO minus Na plus. So this is going to be the ionic head, and this is going to be the covalent tail. Now, let me quickly talk about a micelle over here. When you are going to be having a micelle, what is going to be happening? I will be having a dirt particle. Let's say I am going to be having a dirt on a shirt over here, or some item which is being washed. This dirt particle is generally going to be considered as some kind of an organic dirt. Basically, it's going to be something which is organic, meaning it is a covalent system. So this is going to be attracted to the covalent tail. What is the principle I am using over here? Like attracts like, or rather you can think of it as like dissolves like. That is the idea here. That is a principle I am using in this particular case. So if like is going to be dissolving or attracting like, I will end up having the dirt is going to be attracted to the covalent tail in this case. So how is the micelle going to be formed? A tiny piece of this dirt particle will basically come out. When it comes out, I will end up having this dirt particle. I am going to draw this fellow in this format like this, where I will be having this as the covalent tail part, and this is going to be my ionic head part. So I am going to be having the same molecule represented like this, where this is the covalent tail and the ionic head. The covalent tail will be attached to this particular fellow, the dirt particle, and the ionic head is not going to be available at all. It is going to be on the outside. So we will have the ionic head basically existing on this outside over here. This is going to be the micelle which is going to be formed over here. Now in this micelle, we can basically quickly talk about some properties of this micelle over here. We are going to be having the ionic head is always going to be having a CO minus ending. So this is the CO minus. Na plus is going to be something which I don't care about because it will undergo hydration. It is not in the part of the micelle over here. So each of these guys will have a negative charge. So what can I conclude over here? I can say that this is going to be my entire thing, which is the micelle. So this entire thing is going to be my micelle, which is going to be my actual colloidal particle. So if this guy is the colloidal particle, what is the charge of the colloidal particle here? It is a negatively charged colloid. Of course, that is not really required in the question. Let's have a look at what's happening here. So micelles are formed spherical. Yes, they are formed spherical in shape with hydrocarbon part towards the center of the sphere. Perfectly correct, no problem. They are already getting the correct answer. Micelles are formed spherical, correct, with the hydrocarbon part lying outside. This is wrong. Micelles are formed non-spherical, wrong again, non-spherical, wrong again. Why is spherical shape preferred? Because you're going to be having repulsions. When you're going to be having repulsions, automatically things will basically end up forming a spherical shape. When I say repulsion, what do I mean over here? I mean that there is a residual attractive or repulsive force left over. In this case, it's a residual repulsive force. Think of the water droplet case. If I take rainwater, when it is falling down, it is going to be basically present in the form of a sphere which is elongated downward. Why is it that way? Because you're going to be having surface area being minimum. Why? Because there is a residual force left over. What kind of residual force? An attractive residual force is left over. Here there is a residual repulsive force left over. But the principle remains the same. When you are having a residual force left over, the system will basically end up moving towards a scenario where surface area is going to be minimum. Why? Because surface energy will be minimum, stability will be slightly better. That is the idea there. So, you are going to be having a spherical surface preferred here. So, spherical with hydrocarbon part towards the center of the sphere. Option 1 is the correct answer for this question here. Let's get to the next one. Okay, it looks like there was an error in the 14th question which they had. Let's get to this one. Which of the following proteins is soluble in water? Now, this is a bit more of an interesting question over here. Why? Simply because the other options are quite weird. Albumin you guys should be familiar with, of course. This is the egg protein. Now, is this soluble in water? Yes. It is definitely not completely soluble, but partially soluble. How do you know this? Anybody who has eaten eggs, unfortunately or fortunately, knows this. You don't need to eat egg also. You should have watched any cooking show where they basically beat egg with anything. For instance, if I'm going to be taking egg and I'm going to be adding a little bit of milk, milk is going to be something where water is going to be my dispersion medium in that particular case. Meaning it is going to be the solvent type of system there. So, if I'm going to be adding a little bit of milk and I'm going to be beating the egg, I will have the egg dissolving into the milk beautifully. Alright. Now, the same thing also happens with water. In fact, it will be better if I have a little bit of salt available or salt added. But even without the salt, it will dissolve quite comfortably in milk and in water also. It won't dissolve completely in water, but in milk it will dissolve beautifully well. Which basically tells me albumin is definitely soluble in water. So, this is definitely the answer for this. Let's talk about the other three guys here. Now, when you're going to be having fibrin, myosin and collagen, all three of these are water insoluble systems. Now, all three of these are fibrous proteins. Now, this albumin is going to be something which is going to be a globular protein over here. Globular proteins are generally going to be systems which are transported in the blood, which means they are going to be soluble. The fibrin also has a globular aspect of it in a different structure. When it is going to be having a different aspect, when it is present in blood, where is fibrin seen? Fibrin is mainly seen in a different form in blood, but that different form is soluble in water. When I am going to be having it changing into fibrin, fibrin is going to be the one which is responsible for the coagulation of blood or blood clotting. For instance, let's say I'm having a cut on my hand. If I have a cut on my hand, that blood will basically be leaking out over there. When it is leaking out, fibrin is not present. But after some time, after exposure to air, that same blood will become dried up over there and it will clot that wound over there. When it clots that wound, that time fibrin is produced there. That fibrin, being water insoluble, becomes something which comes out of the blood and clots my cut over there, which is basically the purpose of the fibrin there. It is going to be useful in blood clotting over there, which makes it water insoluble. Myosin is a little bit more trickier, but it is definitely something which is water insoluble as well. Collagen is actually going to be something which most students or other most people our age who are health conscious should know. When I say our age, I mean your age and my age roughly. So, I am a little bit over 33 or 33, 34 now. So, I would say something like anyone who is over 16, 17 years old is going to be somebody who is going to be health conscious. Most health conscious people should know what collagen is going to be. Collagen is going to be the protein, the fibrous protein which is present in our joints. For instance, let's say I'm taking this joint over here in my body. This joint is going to be having a bunch of proteins which are going to be acting as building blocks, which are going to be effectively connecting muscles and the bones over there. Generally, collagen is present in all of those joints over there to give them a nice stretchy characteristic, so that they can move around, they can bend around, and they are still protected quite comfortably. So it gives a stretchy character to those joints, and it gives flexibility to joints generally. If your collagen level is low, your flexibility is going to be very poor. Obviously, in India, that is also something which can be fixed by yoga, etc. Yoga helps in, increasing the flexibility. Of course, collagen is a diet way of increasing the flexibility as well. So coming back to this is of course going to be water insoluble as well, because it is, if it is soluble in water, it should basically be washed away with your blood. The fact that it stays in your joint tells you that it is going to be something which is insoluble in blood, insoluble in water effectively. So the only one which is going to be soluble in water here is the albumin in this particular case over here. Let's get to the next one. Which of the following is not used for a drying agent? Again, this is a very ambiguous question. Why am I saying ambiguous here? I'll explain. Now, when you are talking about drying agent, what do we assume as a drying agent? That is the real problem here. Drying agent, now I am going to base my assumption as something which removes water. How do we remove water? Because it is attracted to water. That is the effective idea in this case. So I am going to be looking at a drying agent as something which is going to be helping me remove water. How is it going to be helping me remove water? Because it is attracted to water. That is the basic principle I am going to be using in this case. So if it's attracted to water, which among these are going to be attracted to water? We can basically try to eliminate options, because this is something which is a slightly weird question. I'll explain why it's slightly weird in a bit. So if I'm going to be using a process of elimination to arrive at the answer, I'm going to be having this guy is going to be similar to what in terms of properties? What do you think it should be similar to? It should be similar to CF2, double bond CF2. What is this guy? This is your Teflon, right? This is going to be in a polymeric form over here. If I have that guy, that is my Teflon over there. So if I'm considering Teflon, you guys know what Teflon is used for. Teflon is what? Non-stick coating. What does non-stick mean? It is going to be not attracted to anything like water or oil. It is going to be repelling all of those guys. So this guy is a repellent coating. Water / oil repellent. Which means if I'm looking at properties, I expect this guy also to be repelling water. Which means not attracted to water. Which automatically tells me it is not a drying agent, according to the definition which I have chosen here, which means this is the answer. Let's check out for the other options also. Now, liquid carbon dioxide. Obviously, carbon dioxide is going to be something which is soluble in water to a decently good extent. How do we know that? We all have drunk Coca-Cola or Pepsi or any carbonated beverage in our life at some point of time. All carbonated beverages will contain carbon dioxide dissolved in water. So this is of course going to be attracted to water. Maybe it can be used as a drying agent, but I am not particularly sure, because I don't think it is going to be realistically used as a drying agent, because liquid carbon dioxide is unfortunately something which is a little bit more expensive than other cheaper drying agents. There are much cheaper drying agents available. Hydrogen peroxide certainly is attracted to water. Removing it from water is very tricky. We will generally end up having it available in the commercial market as a soluble solution with water. So again, this is also definitely attracted to water. CCl4. Of course, it is also going to be attracted to water, because CCl4 can undergo hydrolysis comfortably. Where have you seen CCl4 hydrolysis? In modification of Reamer-Tiemann reaction, I have seen CCl4 hydrolysis, or you should have seen the CCl4 hydrolysis, where if I am going to be taking phenol with carbon tetrachloride and basic medium, I will end up having it dissolving, basically giving me salicylic acid as the product in that particular case. So definitely this also is going to be attracted to water. So all three of these guys are technically attracted to water. Whether they are going to be removing water or not, that is something which is going to be depending on the property of attraction to water, which means if they are attracted to water, technically, logically speaking, they should be able to remove water. Let's come to the last point, which actually gives the answer more efficiently as option 1. This guy is used in dry cleaning. Alright, this guy is going to be used in dry cleaning. You guys should already know, quite obviously, dry cleaning basically means no water. Alright, when you are going to be having, say, something like a rajai or something like a carpet or something which is a good suit, something of that sort which requires dry cleaning, a lehenga or something of that sort, what happens is you need to basically make sure that it is not treated with water and dried the same way. So you need to perform dry cleaning. This is an agent which is used in dry cleaning of, very expensive clothing. So that is basically the reason why we can 100% say it is not going to be a drying agent in this case. This is question 16. Let's get to the next one. Grignard reagent reacts with which of the following to give methane gas? So this guy can react with any acidic hydrogen to give methane gas. That is the basic principle. So if I want this guy to react with any acidic H plus to give myself methane gas here, anything which is going to be capable of giving out an acidic hydrogen to this guy will do the job. Now H2S, certainly it will work, H2O it will work, NH3 also it will work. Let me explain each of the three reactions quickly. So if I have this fellow reacting with H2S, what is formed in that particular case? I will have methane gas plus I will be having HS minus MgBr. This is going to be generated. Next, if I am going to be having water, what will I be having in that particular case? I will be having MgBr OH minus. If I am having ammonia, what is going to be having, present in that particular case? I will be having methane gas, of course, being released, but I will be having in this particular case NH2 minus being generated in this case. So it will be MgBr NH2 minus. So answer for this question is all three of these are correct. All of these is the correct option for this particular question here. Let's get to the next one. Number of sigma bonds in this compound. Of course, the compound is not beautifully represented. Let me directly draw the compound again. So we are having it as this. CH3, single bond C, double bond C. I am having a H over here. I am having another hydrogen over here. I am having another single bond to a carbon here. I am having a triple bond to carbon over here and another single bond to carbon. Single bond to hydrogen. So this is the compound here. Let me confirm that this is the compound. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. I am going to be having a triple bond on this corner and then a double bond over here conjugated. Then we are having a CH3. Beautiful. So let's start counting the number of sigma bonds here. So sigma, 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 sigma. One more sigma here and one more sigma here. So how many sigma bonds are present here? 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So let me just check it up again once. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So in this case here, am I having properly structure being maintained over here? 4 bonds for this guy, 4 bonds for this guy, 4 bonds for this guy, 4 bonds for that guy. Cool, okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Why am I checking a bunch of times here? Because these are questions where mistakes can happen because of stupidity and carelessness. I might still be making a mistake. Let me just count it in that guy. 3, 4, 5, 6, 7, 8, 9, 10. So 10. There are multiple ways of counting. Count whichever way you are going to be confident about your counting over there. You can either draw like this or you can get it counted that way. I basically drew like this to show you guys how to count in a proper structure. I prefer actually counting in that. How do I count in that? There are 3 hydrogens, so 3. 1 hydrogen, so 1. 1 more hydrogen, so 1. 1 more hydrogen, so 1. So I am having 3 plus 4, 5, 6. 6 done. How many bonds are there? One bond over here, one bond over here, one bond over here, one bond over here. Because only one bond will be sigma. The double bond is going to be something where there is going to be 1 sigma, 1 pi. This triple bond is going to be 1 sigma and 2 pi. So I am going to be having 1 over here extra, 1 extra over here, 1 extra over here, 1 extra over here. So 3, 4, 5, 6, 7, 8, 9, 10. That's basically the idea here. So I'm going to be having in this particular case here 10 sigma and 3 pi. So effectively number of sigma bonds in this question here, 10 sigma bonds. This is question number 18. Given structure is going to be. Now, of course, this is going to be something where there is a tiny error here. They have missed out on OH here. The structure is not beautifully, perfectly drawn. Tiny error is there. OH should have been present over there. Chalo, it's okay. Now, in this particular case here, buna N and styrene are straight away out. Alright, buna N and styrene are straight away out because they are going to be copolymers involving different scenarios there. This guy doesn't involve phenol certainly. That is going to be involving a derivative of benzene, but not really phenol. So these two are the cases to look at in this case. Let's talk about both of them. There is only tiny differences between them. Let's talk about them. Let's say I'm going to be having phenol. If I'm going to be reacting this with formaldehyde in the presence of concentrated H plus, a tiny bit of catalytic concentrated H plus, what happens is I will have this fellow basically ending up in the formation of H, C double bond OH plus, the positive charge here, a H over here. This carbon becomes electrophilic. The phenol can then go attack from the para location or the ortho location to perform electrophilic aromatic substitution reaction, which will effectively result in the formation of these guys, OH and a CH2OH, or I'll be having OH over here and a CH2OH over here. Of course, this doesn't stop here because when I have concentrated H plus available, what will happen in that particular case there? I'll be having this OH will get protonated in the process, resulting in the formation of this carbocation. Or I can of course get the other system also. What is the other system in this case? I can get a CH2 plus over here also. So when I'm going to be having both of these systems at play, I can have these guys then go and further perform EAS on phenol. Or themselves. So we will end up having a polymerized product obtained over there. Now, the polymer which is going to be formed can be two types. Now, the first one is going to be bakelite, the other one is going to be novolac. Let's talk about both of them. In the case of bakelite, what is going to be happening is, I will have something like this. I will have an OH, I will have a CH2 link over here, I will have a CH2 link over here, and I will have a CH2 link over here. So I will have a link on this side, and on this side, all directions I will end up having links applicable. So I will be having something which is going to be a thermosetting polymer which is going to be obtained over there, which is going to be the bakelite. Why is it going to be thermosetting? Because you will have a long chain like this with cross links applicable. This is going to be a cross link applicable over here. This cross link is going to be something which makes the bakelite have thermosetting characteristics for sure. The novolac on the other hand is going to be this guy, which is going to be nothing but only the linear part, no cross linking over here. So novolac is going to be pure linear, no cross links. One second, spelling is quite badly wrong there. So we are going to be having the novolac being a linear polymer in this particular case over here, no cross linking. If it has cross links, it is straight away called as bakelite in that particular case. So the answer in this question is novolac. Of course, you need to know the two names, bakelite and novolac, and you need to know the distinction between them. So the polymer obtained over here can be bakelite, which is the cross link polymer, or I can get the linear one, which is of course the novolac over here. Now, the conditions required are going to be different. Alright, we will have specific conditions giving me Bakelite or Novolac depending on what I want to get. This is question number 19. Let's get to the next one. Phenol is going to be doing monobromination at the para location. This is not going to be happening with bromine and H2O. It will also not happen with bromine and FeBr3. It will happen when you are going to be having, in this particular case here, it will be happening when you are going to be having bromine in non-polar solvent or mildly polar solvent. The greater the polarity, the more you will end up having multiple attacks. For instance, if I use phenol with bromine water, you guys should know definitely what is going to be happening in that case. If I am hitting this with bromine water over here, I will be having a tribromo derivative obtained in that particular case, which of course comes out as a precipitate. So I am going to be having this, which is going to be getting out as a white PPT here, is going to be happening because the polarity is higher over here. So I need to use lower polarity. What is generally preferred over here? Bromine in carbon disulfide or carbon tetrachloride are the most preferred. Of course, chloroform is a close relative of carbon tetrachloride. So I can technically say chloroform will also work over here. Or I can also say something like dichloromethane might also work over here to a decent extent. So in this case here, which options are going to be giving me the answer? 3 and 4 are going to be giving me the expected reaction. So if 3 and 4 are going to be giving the expected reaction, answer is going to be option 3 in this case. Remaining are all going to be not applicable. This is question number 20. 21. Reaction of this fellow with Grignard followed by hydrolysis. So this can be understood as simply H3O+. No need to basically fuss about it. It is directly H3O+ in this particular case here. So we are going to be hitting it with Grignard reagent in this case. Let's talk about the principle used over here. Now, we are going to be having 2 locations for attack applicable. There is a reasonably high delta plus on this location, let's call it delta plus 1. There is also a reasonably high delta plus on this location, which is going to be delta plus 2. The delta plus on these 2 locations, if I have to characterize them, delta plus on 1 is going to be greater than delta plus on the second location, which makes location number 1 a harder or stronger electrophilic location. Now, Grignard, what kind of a system is Grignard over here? If I am considering Grignard or alkyl lithium, these 2 guys are going to be having a very high delta minus on the CH3 in this particular case here. So both of these are going to be having very high delta minus on the CH3 here. So very high delta minus, which makes them powerful nucleophilic systems. So you can think of them as hard nucleophiles. Now, how do you categorize something as hard or soft? If the delta plus is focused on a location, we can call it as hard. If the delta minus is focused on a location, you can call it as hard as well. So when a particular location is going to be having a focused charge density, we end up calling it as harder. The hard will have a meaning only when there is a soft attached. If I have only one electrophilic location, there is no meaning to calling it as hard or soft. That's just nonsense. You will have hard having meaning when you have a soft location also available. So for instance, if you are having a categorization of a good nucleophile, what is the point of calling something a good nucleophile when that's the only nucleophile? If only one nucleophile is going to be known, we don't call it as good or bad. We can call it as good or bad when we have other nucleophiles also taken into consideration. When I'm comparing, then we can call it as good or bad or hard or soft. So in this case here, we can say that the delta plus in the first location is higher, hence it is harder, whereas this is going to be softer electrophilic location. Now, so if I'm taking Grignard or alkyl lithium, we will end up having them being a hard nucleophile. Whereas if I take, say, something like dialkyl lithium cuprate. This fellow here, the delta minus is lesser. Lesser delta minus. Because it's going to be having lesser delta minus, we will end up having this being a softer nucleophile. What does softer nucleophile result in? It attacks softer electrophilic location, which means it attacks delta plus 2. Whereas the Grignard or alkyl lithium are harder nucleophiles attack harder electrophilic locations. Implies this guy is going to be attacking which location? It attacks delta plus 1. So, I will end up having attack on delta plus 1 now. What does that mean? I will be having this guy attacked over here. CH3 minus will attack. This will shift over here, resulting in the formation of C double bond C, single bond C, single bond C, single bond C, O minus. That O minus with H3O plus will end up becoming OH. So, this is going to be the product in question here, which is going to be option Bombay. Now, the principle which I am using here is hard, soft, acid, base. Let me basically make it more blunt and clear. Hard nucleophile likes to attack hard electrophile, whereas soft nucleophile tries to attack softer electrophilic location. That is the basic principle. Let's get to the next one. So, in this case, answer is going to be option 2 over here. If I use dialkyl lithium cuprate, it will end up doing 1,4 addition. In a similar way, another softer nucleophile is going to be your enolate ion. If I have an enolate ion available, this is going to be something where this will have resonance. So, when it is having resonance over here, this will basically end up showing two structures. So, this will be harder nucleophile because the delta minus is more focused here. This will be softer nucleophile. That is the idea here. So, the enolate ion will perform 1,4 addition here. So, if I am doing an aldol type, it will do 1,4 addition. If it is going to be something which is going to be the given question, 1,2 addition happens here. Let us get to the next one. Primary aromatic amine can't be prepared by Gabriel thalamide method. Let us talk about this now. What does primary aromatic amine mean? Let us take a simple example. This is a primary aromatic amine, aniline. Aniline, they are telling, cannot be prepared by this particular method. Is that true? Yes, it is true. Assertion is true. In all three of these, assertion is true is correct. So, fourth option is wrong. Let us look at the reason why this cannot be done over here. They are telling us aryl halide cannot undergo nucleophilic substitution reaction. Let us talk about what happens in a Gabriel thalamide synthesis there. We are going to be having thalamide. This is my thalamide. So, thalamide ion is an N minus here like this. This N minus is going to be reacting with, say, let us talk about chlorobenzene. Can this reaction happen? That is, N minus comes and attacks here. This attack cannot happen. Why? Because the benzene ring will repel nucleophiles. This is electron rich, repels nucleophiles. And more critically, this carbon chlorine bond is going to be having partial double bond character, which makes it difficult to break as well. So, the idea is very simple. You will end up having in this case no reaction. What is the reason for no reaction over here? Because nucleophilic substitution cannot happen, cannot undergo nucleophilic substitution reaction. This statement is correct and it is the perfect reason. So, reason 2 is going to be true over here. This is also true here. Reason 2 is false is wrong. Reason 2 is not correct, that is wrong. It is the correct explanation. Answer is option 1 in this particular case here. So, we are going to be having the reason why this is not possible. That is the first statement, assertion is correct over here, is because nucleophilic substitution cannot happen on the benzene ring. Why does it not happen? Because the benzene ring is electron rich, it repels away my nucleophile in this case, and more critically, we are going to be having partial double bond character, which is going to be present between the carbon on the benzene and the halogen over there, which makes it more difficult to break. Both are going to be effectively saying that the reason given here is correct. Let's get to the next question.
Which of the following reacts with sodium bicarbonate and evolves carbon dioxide gas? Let's talk about what happens in this process. When I have NaHCO3 reacting with an acidic hydrogen, what happens there? The NaHCO3 technically is going to be something which will break up as Na plus HCO3 minus. This HCO3 minus ends up reacting with my acidic hydrogen in reality. So when these two fellows combine, they will actually become H2CO3. That H2CO3 is going to be something which is unstable and it will end up becoming H2O plus carbon dioxide gas. This is the process by which your NaHCO3 evolves carbon dioxide gas. So when NaHCO3 is going to be reacting with an acidic H plus, it can give out carbon dioxide gas. But there is a question here to basically answer internally. Effectively, where should this acidic hydrogen comes from? This acidic hydrogen should be from any acid stronger than H2CO3. Why? Because when this guy accepts the H plus, it becomes H2CO3. That means if the acid in question in original case, from where the acidic hydrogen is removed, is weaker than H2CO3, it cannot do this reaction. So this test is answered by any acid which is stronger than H2CO3. So the NaHCO3 test is answered by all acids which are stronger than H2CO3. So answered by all acids stronger than H2CO3. That is the basic idea. Obviously, this is going to be one which will be certainly answering them. In this question here, you don't even need to know whether the test is answered or not. All you have to do is choose the strongest acid, because it's a single correct answer. So choose strongest acid. If it was a more than one answer correct question, the question becomes more trickier. But this is a JEE Mains question. When it's a JEE Mains question, your job becomes very simple. Choose the strongest acid. You don't need to worry if these guys are going to be reacting, because this is the strongest among the bunch. So if any one of those guys will give the reaction, this will absolutely give the reaction also, which means the answer has to be option 1 anyway in this case. So the question can be interpreted as choose the strongest acid, which is going to be option 1. Now I think this brings us to the end of the paper, or the end of the number of questions which we already have collected over here. So thank you very much for your patience, guys. I hope you found this discussion meaningful and useful. Good luck with your JEE Mains examinations and other examinations. Take care, stay safe, wear a mask. And if you can get vaccinated, please do so.